We will study higher order differential equations from now. Before this, we were studying first order linear differential equations, but now we have moved to higher order differential equations. Now, suppose we have a variable income, a variable that is income, and then after that, what happens is, okay, let me make it a little bit. Yeah, now we have a variable income that is it is denoted by y. Now the rate of change of y is known as the first order derivative of that variable with reference to any other independent variable, whereas the rate of change of the variable income is referred to as the higher order differential equation of this variable income. Therefore, if we say that if we write it as dy by dt. Now this is the first order differential equation. If we take the higher order differential equation of this function, we get d square y over dt square. If we want to take further the highest differential equation, then we take the third order derivative of this function, and then we get dy cube divided by dt cube. These are the higher order differential equations of this function. Now any differential equation of order n is given by, that is when the highest order of the function, highest order derivative of the function is n, then we have dn y divided by dtn, okay, dtn plus, then we have a1. A1 is playing the role of coefficient over here. Then the next derivative is n minus 1 of y divided by, that is it is differentiated with reference to dt raised to power n minus 1. In the same way, it will become a2 dn minus 2y divided by dt n minus 2 and so on. And in the end, what will we get is, we will get a n minus 1, the last value of coefficient for this function, and the first order derivative in the end will appear, that is dy by dt. Over here we will have n minus n, therefore we will have, oh sorry, no, over here we will not have n minus n, rather we will have a n minus 1 dy by dt plus a n y. Yeah, now over here we will have no derivative is equal to b. Over here we will have, if we write dy by dt, we will have n minus n, and dy by dt will diminish from here and there, therefore we will get a and y is equal to b, that is b will appear over here. Now suppose n is equal to 4, the highest order derivative is 4, d4y divided by dtn plus a1, d4 minus 1 is 3, so therefore the second highest order derivative will be d3y divided by dt3, and in the end we will get the last value of a into y is equal to b. Okay, now let's move forward. In the simple terms, when we write it like this, is a bit complicated form. Now let's write it in its simplest form, that is we will get yn, that is the variable y is differentiated nth time with reference to the variable t, plus, then for the second one is, suppose this was 4, second one will be a1 y raised to power n minus 1, okay, and it is again differentiated with reference to the variable t, and in the end what will we get is that when we move ahead we will have an minus 1 y prime of t, the first derivative only over here, and then in the end what will we get is, we will get a and y is equal to b. The simple function that was given, that is, it has not been derived over here. So this equation is of order n because nth derivative is the highest order derivative. It is linear only because dependent variable y appears in the first degree, and there is no product term occurs in which y and any of its derivatives are multiply. Okay, suppose we have a second order linear differential equation, and we are studying it with reference to the constant coefficient and constant term. Now we move on towards our next topic, that is second order linear differential equation with constant coefficient and constant term. Okay, what is this statement saying? Now the most notable higher order differential equation is second order differential equation, and second order differential equation is the one in which the highest or the higher order derivative or differential involved is the second order derivative, that is the value of n is equal to 2. Therefore, if we take a simple example, what we get is the example of the statement that has been written over here. It will become d square y divided by t square. This is the highest order derivative for this function. Suppose we have a negative sign in between, and then we get the value of a to be 10, and then n minus 1 will become 2 minus 1 is 1. Therefore, it will become only dy by dt, plus then we have the next value of a, that is, suppose it is 6, and here we will have y is equal to 35. Suppose this is just an example. Here we have d square y divided by dt square. Here we will have d raised to power 2 minus 1 y divided by dt, plus over here we will have 6 into dy raised to power 2 minus 2. Therefore 2 minus 2 will become equal to 0. Dy by dt will diminish, and therefore we will get 6y only over here is equal to 35. Okay. Now this equation is describing the rate of change of the variable y. For this we require time path, that is time period t. General form of this equation is d square y over dt square. Now here this 10 is referred to as a1 and this 6 is referred to as a2. And what is 35? 35 is b. Now again we can write this equation in a more simplified form, that is it will become now y double prime of t plus a1 into y prime of t. This is y prime of t plus a2y is equal to b. a2y. Now we do not associate any t over here because over here we have not taken any derivative. So therefore this 10 is a1, this 6 is a2, and this 35 is b. If we want to interpret them, we will have a1 and a2 as coefficients, and b is simple a term. Now if the value of b is equal to 0, then what happens is that we say that we are dealing with the homogeneous case. And if it is not equal to 0, then what we are saying, we are dealing with non-homogeneous case. When the value of b is equal to 0, we are dealing with the homogeneous case. When it is not equal to 0, we are dealing with the non-homogeneous case. Now we are mostly concerned with the non-homogeneous case where the value of b is not equal to 0. We are mostly concerned with this situation where b is not equal to 0. Therefore, we are concerned with the non-homogeneous case in which solution of equation yt is yc plus yp. We know that when we were studying the non-homogeneous case earlier as well, we found out that yt is equal to yc plus yp. What was yc? Yc is the complementary function, whereas yp is the particular integral of the function. Yp provides the equilibrium value of y in the intertemporal sense, and yc represents the derivation of the time path yt from the equilibrium. We have studied this whole in detail in the previous lectures. Now how to find yp? Let's find yp. Suppose we have that same function, that is, let's move over here. This is y2. Okay. we have this function y double prime of t plus a1 y prime of t plus a2y is equal to b. Now in order to find out yp, what will we do is that we will say that y double prime of t is equal to 0. Okay, and then we will also consider y prime of t equal to 0. Both the derivatives are taken to be equal to 0. Then what happens is that 0 plus a1 into 0 plus a2 into y is equal to b. Therefore, after this, what we'll get is that by keeping y over here at this particular point, we get y is equal to b over a2. So therefore, the value of the second coefficient in second order differential equation should be divided by the value of b, that is the term, and which is non-zero term. Therefore, y is equal to b divided by a2. This is the value of particular integral. Okay, now let's stop it over here, and after this, in the second or the next lecture, we will find out the value of yc, which is a bit uh, lengthy and complicated procedure. For that, we will make another video. Thank you.